Hey all, so in this video I'll be going over the 2024 NHT physics exam and the short answer section. So without further ado, let's get started. So the speed v of a charged particles can be measured by passing them through a combination of electric and magnetic fields that are perpendicular to each other. There is an electron enters the space between two parallel charge plates P and Q, where there is a magnetic field B directed into the page as shown in figure 1. Ignore the gravitational forces. Okay, the electron passes between the charged plates and is undeflected. Determine the polarity of the charges on P and Q. Okay, so for this question, what I want you to do is we're going to be using the right hand slap rule, I think it's called. So we point the thumb in the direction of velocity, so to your right, and then the finger should be pointing into the page, as that is the direction of the magnetic field. And you will notice that the force that is coming out is like this way, okay? But keep in mind that this is an electron, so it will be flipped, so the electron will be facing the force that is this way. So the path, if the electron were to deflect, the path would be like this, okay? But since electron is not deflecting, the polarity of Q would be negative, right? Because that means the electron would repel because it's the same charges, so this will provide the upward force and therefore it will be undeflected, okay? So that is the reasoning. All right, so Q will be negative and P will be positive. So let us write that down, okay? So P is positive and Q is negative. Okay? By using the right hand rule, it can be determined that the force due to magnetic field is pointing downwards, right? Is pointing downwards, as we discussed already, right? If you remember, by using the right hand slap rule, okay? And to balance it out, the force due to electrical field needs to point upwards. Therefore, Q is negative and P is positive. And P is positive. Okay, so this is the answer. All right, let's move on. So when the electron has a speed of this and the electric field strength is this, the electron is undeflected as it travels between the charged plates. Calculate the magnitude of the magnetic field if the electron is undeflected. Okay, so for that, we know that our net force is equals to 0, right? That means the force generated by magnetic field has to be the same as force generated by electric field. So we'll have BQV is equals to QE, right? So this and this will cancel out, leaving us with B equals to E on V. Now, let's just substitute the numbers in. So our B is equals to 2.4 times 10 to the 4 over 1.2 times 10 to the 5. Let me get my calculator. Okay, let's type that in. So 2.4 times 10 to the 5. 4 times 10 to the 4 divided by 1.2 times 10 to the 5. And we will get 0.2. So 0.2 Tesla. Okay? The electron is now replaced by a proton traveling at the same speed. What changes, if any, are required so that proton is also undeflected as it travels between the charged plates? Explain your reasoning. Okay. So if I were to go back to this diagram, now this is our proton. Okay, no more electrons, so proton. Now what we'll do is, again, we'll use the right hand rule. So thumb points in the direction of velocity, fingers pointing into the page, as that's where the magnetic field is, and you'll see that the force is going to be upwards this time. And this time we don't need to flip it because it is a proton, not an electron. So if it were to deflect, the proton would go in like this. Okay? Now, since this is already positive, it will provide the repulsion so that proton is undeflected. So in short, we don't have to change anything, basically. So let us write our answer down. No changes are required. Because again, using the right hand rule and rule, it can be determined that the force due to magnetic field is pointing upwards, is now pointing upwards, and force due to electric fields is now pointing downwards with the same magnitude, of course, with the same magnitude. Okay, so that is the answer for this question. Hopefully this made sense. Question number 2. Himawari 8 is an equatorial weather satellite. Okay, it orbits the Earth at a constant radius of this over here. From the center of the Earth, as shown in figure 2, the mass of Himawari is 1300 kilogram. Assume that the orbit is circular. Okay. Calculate the magnitude of Earth's gravitational field at the orbital radius of Himawari 8. Give your answer to 3 significant figures and show your working out. So we just have to use one formula, which is G equals to Gm on R squared. Okay. So our G is just a constant, so 6.67 times 10 to the negative 11 times by the mass of Earth, which is 5.98 times 10 to the 24, divided by R, which is the altitude or the radius, which is 4.22 times 10 to the 7 and whole squared. Alright, so let's calculate that. So 6.67 times 10 to the 11, negative 11. 6.67 times 10 to the negative 11 times by 5.98 times 10 to the 24. And then we have 4.22 times 10 to the 7. 7 times 7 squared. So we get 0.226 Newton per kilogram. So 0.226 Newton per kilogram. Okay? Show that the period of Himawari 8 is 24 hours. Show you're working. Okay. So in that case, we know that G is equals to 4 pi squared R on T squared. So that means T squared is equals to 4 pi squared R on G. So a T is equals to square root of the whole thing, so 4 pi squared R on G. So now we just substitute the numbers in, so we have 4 times pi squared times 4.22 times 10 to the 7 divided by 0.226 as we calculated from the question. Okay, so 4 times pi squared times 4.22 times 10 to the 7 divided by 0.226. Okay, and that gives us 85,836.48 seconds. Okay, now we're to convert it into hours, so we just divide it by 3600. So 85836.48 divided by 3600, and we will get 23.84, which is roughly 24. So roughly 24 hours. Okay. Juan calculates the gravitational potential energy, e.g. of the Himawari 8 satellite in orbit, and uses the working. Okay, alright, analyze Juan's use of gravitational potential energy formula for Himawari 8 satellite in the orbit. So, Juan is clearly incorrect because of this over here. He assumes that the gravitational force is going to be the same at an altitude of this as it is on the surface of the Earth. So that's where his calculation went wrong. So that is not going to be correct answer. So we can say Juan is incorrect. So Juan's calculations assumes that G at the satellite altitude is the same as it is on the surface of the Earth. This is not the case, as G is inversely proportional to 1 on R squared, meaning that as R increases, G decreases. Okay, hopefully this made sense. Alright, so question number 3. Alright, so a 4-meter long vertical copper pole acts as a lightning conductor on top of a skyscraper, as shown in figure 3. The lightning conductor is located where Earth's magnetic field B is horizontal and points directly north. The magnitude of Earth's magnetic field at the location of the lightning conductor is this. Okay. During an electrical thunderstorm, a lightning bolt produces a current of this downwards in the lightning conductor. Calculate the magnitude of the force acting on the lightning conductor where there is current in the lightning conductor. While there is current in the... Okay, so we can just use this. F is equals to BIL. So magnetic field was given to be, what is it? Phi times 10 to the negative 5. Our current is 4 times 10 to the 3. And our length is going to be 4 meters. Okay. So let us calculate that. So we got 5 times 10 to the negative 5 times by 4 times 10 to the 3 times by 4. So we get 0.8 Newton. Okay? Alright. The vertical copper pole is increased in length and is again hit by a lightning bolt that produces a current of 4 amps downwards in the lightning conductor. Describe what effect, if any, this increase in length will have on the magnitude of the force acting on the lightning conductor while the current is present. Justify your answer. Okay, so we use the formula F equals to BIL. Now, as you can see, that force is going to be proportional to the length. So therefore, as F increases, therefore as L increases, not F, L increases, we're talking about the length. Well, F also increases. F also increases. Okay. Another flash of lightning is measured to have a voltage of 500 kilovolts between the ends of the pole and the current this in the pole for the duration of this. Okay. Calculate the total energy transferred from this lightning bolt to the pole during the lightning strike. Alright, so we know that E is equals to PT, okay, power times time, and P is equals to VI, so we can write E equals to V, I, and T. Now we can just substitute the numbers, so 500 kilovolts, which is going to be 500 times 10 to the power of 3 volts, times the current, which is 8 times 10 to the 4, and then 120 microseconds, which is 120 times 10 to the minus 6. Okay, so if I were to calculate that, we got 500 times 10 to the 3 times by 8 times 10 to the 4 times by 120 times 10 to the minus 6. Okay, so we have 4.8 times 10 to the, to change my mode to scientific. Okay, so 4.8 times 10 to the 6 joules should be your answer. Okay, all right, so question number 4. A simple electricity generator is shown in figure 4 below. When the coil is rotated with a frequency of 10 Hz, the output voltage across the slip rings is measured. All right. The graph in figure 5 shows how the output voltage varies over time for 2 cycles. Calculate the period of the generator. Well, we know that period is equals to 1 on frequency, so that is just 1 on, what is it, 10? Yeah, 10. 1 on 10, which is equals to 0.1 seconds. Okay? 0.1. Alright, the frequency of the generator is now halved to 5 Hz. The coil commences rotating from the same position as shown in figure 4. On figure 6 below, sketch the new output voltage. The original waveform is shown as a dashed line for reference. Okay. So since the frequency has halved, the period would be doubled, right? Because they are inversely proportional to each other. And since the period has doubled, that means the same amount of flux change happens over a longer time. So that means the induced voltage must be halved as well. So rather than having 4 volts as peak, it will now be 2. Okay? And it will be like here, and then here, and then here, and then here. Yeah, because the amount of change in flux, now, like the same amount of flux, right? It's not even different. So the same amount of flux change happens over a longer periods of time. So the induced voltage is going to be lower. Okay? So it's going to be like, okay, that is already like that. No. Okay, this is going to be a challenging graph to draw. Okay, I guess this will do, but yeah. Okay, this should be your answer. So yeah, okay, I think this should be it. Right, the frequency is now returned to 10 Hertz. The slip rings are replaced with a split ring commutator. Sketch the new output voltage on figure 7 shown below. Assume that the coil commences rotating from the same position. Okay. Okay. So now rather than having, yeah, it was just going to be that. And then now we just have to copy and paste it. Copy, paste. That, paste, that, paste, and like that. Okay. That's going to be our graph with the split ring commutator. Alright, question number 5. Mass spectrometers are used to separate charged particles of different masses. Two masses P and Q have identical charges but different masses. Okay. Both particles enter the uniform magnetic field B inside the mass spectrometer at the same point at the speed of this over here. Okay. The particles travel in circular arcs that have different radii and strike a detector at different places. The path of P and Q are shown in figure 8. Which particle P or Q has greater mass? Okay, so we know that R is equals to mv on qb. Okay, and everything is constant essentially, except the mass. So in that case, we know that R is proportional to the mass, right? So that means the larger radius will have more mass. So that means P has greater mass. Okay, so answer is going to be P. Okay, the strength of magnetic field B inside the spectrometer is 0.01 Tesla. Particle P has a charge of 3.2, okay, and moves in circular path of 0.64 meters. Calculate the mass of particle B. Okay, so we are going to be using the same formula again. So we know that R equals to mv on qb, right? Yep. And we have to solve for m, so let's make m the subject. So R qb on v. Okay, so radius is going to be 0.64 times by q, which is 3.2 times 10 to the negative 19, and times by b, which is 0.010, all over velocity, which was given to be what? 2.5 times 10 to the 4. So 2.5 times 10 to the 4. Okay, now let's put this on our calculator and see what we get. So we will have 0.64 times 3.2 times 10 to the negative 19 times by 0.010 over 2.5 times 10 to the 4. Okay, so we get 8.192 times 10 to the minus 26 kilograms. Okay, 8.192 times 10 to the minus 26. All right. Question 6. A small bar magnet is moved at a constant speed through which the middle of a circular wire loop, as shown in figure 9. Okay, an EMF is generated in the wire loop. The wire loop is connected to two terminals A and B. Okay, explain why an EMF is generated in the wire loop. Very well. So according to the I'm using a different color for written explanation. So according to Faraday's law, a change in magnetic field induces an EMF, right? Induces an EMF. So that means as the magnet approaches the loop, the loop experiences, as the magnet approaches the loop experiences a change in flux, and hence an EMF is generated. Okay? Alright, so according to Faraday's law, change in magnetic field using the EMF, okay, as a magnet approaches the loop, okay, change in flux, and okay, cool. As the magnet approaches the loop, current flows in the loop. As viewed from the left in figure 9, does the current flow clockwise or anti-clockwise? Okay, cool. So using the right hand rule, if I were to put my thumb there in the direction of v velocity, and as you can see, the fingers are curling in the clockwise direction, right? And now of course this is not going to be the case, because moving the magnet to the right moving the magnet to the right is generating clockwise current, increasing the flux towards the right. So that means to oppose that, according to Lenz's law, to oppose that, we have to oppose the change in the flux. So that means now we have to point the finger to the left. Now to point the thumb to the left, and as you can see that now the fingers are curling the anti-clockwise, right? So our current generated will be anti-clockwise, if that makes sense. Okay, so I'll explain again. So since our magnet is going to the right, there will be an increasing flux pointing to the right, and of course to oppose that, a flux pointing towards the left will be generated. So that means our induced current will be anti-clockwise. Okay. All right, so let's put that in words. So as the magnet moves towards the loop, the loop experiences increase in flux to the right, by Lenz's law. The induced magnetic field opposes this change in flux, and hence the current will generate an increasing flux to the left. And using the right hand rule, an anti-clockwise current will be produced, or maybe will produce flux pointing to the left. Okay, hopefully that made sense. Yeah. Okay, on the graph below, sketch the EMF generated in the loop as a function of time from when the magnet begins to the left of the loop as it goes to the loop to when it is to the right of the loop. Okay, so, well, as it goes closer to the loop, it's going to face an increase. It's going to face an increase like that, and then it's going to stop, and then that's where, and then as soon as it's in the middle of the loop, it's going to drop down to 0, and as it goes to the right, it's going to face a slight increase again like that. Okay, can't draw graph smoothly, something like that. Okay, so it's basically like a sine curve essentially. All right, so question number 7. Aisha is learning to play tennis. She throws the ball vertically upwards, and when it is at its highest point and stationary, she hits it with the table tennis bat. Okay, the bat hits the ball horizontally as shown in figure 10. At the moment of collision, the bat has a speed of 2.5 meters per second. The mass of the table tennis bat is 0.2 kilograms, and the mass of the table tennis ball is 3 times 10 to the minus 3 kilograms. On figure 10, draw vectors to show forces acting on the ball at the moment it collides with the bat. Include the labels to show the cause of each force. Okay, very well. So first one, of course, there will be gravitational force like this. Okay, and then actually let me draw that in red color, and then we go red. Okay, and then there will be a force exerted from the bat to the ball. Okay, like that. So we can just say F earth on ball, and then F bat on ball. Okay, on figure 10, draw and label the normal force according to Newton's third law resulting from the force of the bat on the ball. What? On figure 10, draw and label the normal force according to Newton's third law resulting from the force of the bat on the ball. Oh, it's just equal and opposite. Okay, so it's just gonna go this way. Yeah, like that. Actually, let me just copy and then paste that, and then paste. It's gonna be like that. Okay, they're going to be equal and opposite in terms of direction. So F ball on bat. Okay. Okay, the bat slows down to 2.4 meters immediately after the collision. Calculate the speed of the ball immediately after it leaves the bat. Okay, so this is the conservation of momentum now. So we know that m bat times u bat plus m ball times u ball is equals to m bat times by v bat plus m ball times by v ball. Okay, so our initial mass of the bat, which is 0.2, times by initial velocity of the bat, which is I think 2.5. Yep, 2.5 plus mass of the ball, which is 3 times 10 to the minus 3, and initial velocity of the ball is just simply 0, is equals to the mass of the bat, which is 0.20, times by the final velocity of the bat, which is 2.4, plus mass of the ball, that doesn't change, times 10 to the minus 3, times by v ball, because that's what we are finding. Okay, so in that case, we will have 0.5 is equals to, let's calculate this, so 0.2 times 2.4, 0.48, plus 3 times 10 to the minus 3 v ball. Okay, so in that case it will be 0.5 take away 0.48 divided by that. So let me just put it in my calculator. Okay, and that gives me an answer of 6.67. So v ball equals to 6.67 meters per second. Okay, 6.67. All right. Explain why gravitational force acting on the table tennis ball can be neglected in the collision. Okay, very well. So I guess the gravitational force compared to the force exerted by the bat is going to be quite minute, right? The gravitational force is going to be quite small compared to the force that is exerted on the ball by bat. And then the other thing is that during this collision, there's only velocity pointing horizontally, and then there is no vertical velocity either. Meaning that the change in the horizontal momentum will be quite significant, while there will be little to no change in the vertical direction. So I guess that's why gravitational force can be neglected. Okay, hopefully that made sense. Now we just have to put in the words. So we can say that the gravitational force on the ball is quite minute, or maybe I can just say quite little compared to the force exerted by the bat. And then furthermore, during the collision, there is only horizontal velocity, implying a significant horizontal momentum. With little to no change in the word hold on. So furthermore, during the collision, there is only horizontal velocity, implying a significant horizontal momentum, but little to no vertical momentum. And hence, gravitational force can be neglected. Gravitational force can be neglected. Can be neglected. Okay. Okay. Many dog owners use ball throwers to throw tennis balls along the way, which their dogs can then retrieve. The student Olaf uses a ball thrower to investigate projectile motion. Okay, Olaf launches a tennis ball with a speed of 30 meters per second at an angle of 15 degrees above the horizontal and from a height of 2.1 meters as shown in figure 11. Okay, ignore resistance for part A, B, and C. Show that the initial horizontal speed of the ball is 29 meters per second. So initial horizontal speed. So that means we are calculating ux, which is equals to initial velocity times the cosine of the angle. So we have 30 meters times by cosine of 15. And that is equals to, let's calculate, that should be equal to 29 times cosine of 15. Okay. Yep, roughly equals to 29. So 29 meters per second. Show that the vertical speed is going to be this. So that is just going to be uy, which is equals to 30 sine 15. Again, let me put that in my calculator. So 30 times sine of 15. Okay, that should be, yep, 7.76 meters per second. Okay. All right. Okay, so calculate the maximum height of the ball above the ground. Okay, so we can just use the silhouette equation. So we can use vy squared is equals to uy squared plus 2ay times sy, right? And what we are finding the maximum height. So we are finding this over here. Okay, so let's make that the subject. So sy is equals to vy squared, take away uy squared divided by 2 times ay. Okay, so now for it to reach the maximum height, that means the final vertical velocity component would be 0, right? Because that's where the maximum height occurs. So that will be 0 squared minus the initial vertical velocity, which is 7.76 squared divided by 2 times minus 9.8. Okay? And that should give us the answer. Okay, why did I put minus here? Because I'm taking downwards as negative, so that's why that is minus. Okay? Alright, so we have that whole squared. Okay, I've messed up my calculations a little bit. That, okay. So that whole squared divided by 2 times 9.8. So we get roughly 3.1 meters. Okay? And of course, this is not going to be the maximum height. The maximum height is going to be 2.1 plus the 3.1, okay? So then we can say adding initial height, and then we can do 2.1 plus 3.1, that is equals to 5.2 meters. So I think this is going to be a final answer, 5.2 meters. Okay? So explain the effect that air resistance would have on the maximum height reached by the tennis ball as calculated in part C. Okay, very well. So now that we have air resistance, the maximum height that is reached by the ball would be reduced, because now obviously it is going to be slowed down by the air resistance. So that's going to be our answer. So the maximum height of the ball would be less than 5.2 meters, as the ball is now slowed down by air resistance. Okay. Okay, question number 9. So in a thought experiment, a very fast train of proper length 700 meters passes through a tunnel, mn, okay, while traveling at a speed of 0.9 times c, okay. Adina, a train spotter, watches from nearby. Adina can see both ends of the tunnel as shown in figure 12. Show that the Lorentz factor for the train at this speed is 2.24. Okay, so this is just putting in the formula. So Lorentz factor is equals to 1 divided by 1 minus velocity squared on c squared, which is the speed of light squared. So that is equals to 1 divided by 1 minus 0.9 squared times by c squared on c squared. So this and this would cancel out, leaving us with 1 on 1 minus 0.9 squared. And now if I want to put that in our calculator, so 1 on 1 minus 0.9 squared. That'll be 2.294 as required. Okay? Adina sees the train enter the tunnel. MN of proper length 700 meters as measured by observer who is stationary with respect to the tunnel. Will Adina see both ends of the train when the front of the train emerges from position N of the tunnel? Justify your answer. Okay, so what Adina will see is going to be a contracted length. So high chances she won't be able to see the train, but let us show some calculations to support first. So L is equals to L0 on Lorentz factor. So the proper length is going to be 700 and our Lorentz factor is 2.294. Yeah, so definitely not. She's not going to be able to see the train, okay, front and back, because it's going to be contracted length that she will be seeing. So the length that she will be actually seeing is going to be 305 meters actually. So for her, the length of the actual train would be 305 meters, which is obviously less than 700 meters, right? So we can say this is the contracted length. Okay, now to justify our answer, we of course need to tell. So Adina will not see both ends. She will see contracted length in her frame of reference, 5 meters, in her frame of reference, okay, since the contracted length of the train is less than the actual length of tunnel, 700 meters. Adina will not see both ends of the train. Adina will not see both ends of the train. Okay? Alright. Okay. Question 10. A 0.5 kilogram ball swings in the horizontal circle at the end of 1.6 meter cord attached to the pole, as shown in figure 13. The cord makes an angle of 30 degrees with the vertical pole. Okay, show that the magnitude of the tension in the cord is 5.7 newtons. Okay, very well. So there is going to be tension in this row over here, and there is going to be the gravitational force, so mg. So that means that the vertical component of this tension force, so this entire thing is tension, so the vertical component, this one, has to balance out with mg, right? And what is the vertical component of this tension force given by? It's going to be T cosine of 30, okay? Alright, so we can say T cosine of 30 is equals to mg, and our tension is going to be mg on cosine of 30. Wait, let me just see, it's cosine of 30, right? So finding this over here. Yeah, okay, just making sure. Don't want to make a silly mistake. Okay, so our m is going to be 0.5 times 9.8 divided by cosine of 30. So that will give us, if I were to just put that in our calculator, 0.5 times 9.8 divided by cosine of 30. So that is giving us 5.65, which is 5.7. Calculate the magnitude of the acceleration of the ball. Okay. And of course, if I were to expand on this, there will be a horizontal component of the tension as well, like so. And that has to match the centripetal force, right? So we will have Fc is equals to T sine of 30. Okay. Then we have M times A of C is equals to T sine 30. Okay. So that means our acceleration would be T on M times sine of 30. So we will have 5.7 divided by M, which is 0.5 times sine 30. I mean, this and this would cancel out, but yeah, so answer should be 5.7 meters per second squared. Okay? Oh, I already have the units. Okay, cool. Okay? Alright, because that is the centripetal force is the only force that is acting in the horizontal direction, because it's a circular, it's a horizontal circle, so centripetal force is going to be there, and that's the only horizontal force, and that has to balance out with the horizontal component of the tension force. Okay? Alright, so calculate the speed of the ball. Now, we know that our acceleration, centripetal acceleration, is given by v squared on r. Okay, so that implies that v squared is equals to ACR. So v is going to be square root of that. Okay, so we'll have 5.7 times, what is our radius? Okay, so well, the radius is not given to us directly, but we can easily calculate because we have a triangle where this angle is 30, this is given, and we have to find this over here. So that is just going to be sine of 30, well, 1.6 sine of 30. Okay? So we'll have 1.6 times sine of 30. Alright, so let's calculate that. So 5.7 times 1.6 times sine of 30. We will get 2.14 meters per second. Okay? Alright. Okay, so question 11. Two pulses P and Q, each with the same wavelength but with different amplitudes, are traveling in opposite direction at speed v. The amplitude of pulse P is double the amplitude of pulse Q. A short time later, the two wave pulses are at the position shown in figure 15 below. Okay, in the box shown in figure 15, sketch the wave pulse resulting from the combination of the wave pulses P and Q. So they will basically add up. The amplitude of them will basically like add up, right? So this is going that way. So wait, let me draw this. Okay, so now this is going this way. Now assuming that they collided here. So this is positive amplitude, this is negative amplitude. So it will generate a wave which is like this. Basically the same amplitude here, essentially. Okay? Hopefully that made sense. Alright, so our wave should just look like this. Or even better, I'll just trace this one up. Yeah, I can use this way. You guys can't, unfortunately, in the exam. Alright, yeah, this should be good. Okay, so yeah, it's just amplitudes adding up. One is positive, one is negative, so they will cancel out and we'll get a positive one. Like, because this is twice, right? So if this was twice, so let's say this is 2 and this is 1, our resultant would be just 1. Okay, that's what's happening. Okay? Explain the production of the waveform you have just sketched in part A. State the physics principle involved. Okay, so the principle involved is known as superposition. Is known as superposition with the resulting wave being the sum of the amplitudes, being the sum of the amplitudes. Okay? Alright, so figure 16 shows below a ray of light entering from air in an optical fiber that consists of two transparent materials, the core and the surrounding cladding. The core and cladding have refractive indices of 1.5 and 1.47 respectively. The ray is incident on the air core interface at an angle of incidence of 24 degrees. Show that the critical angle for core cladding boundary is 78.5 degrees. Okay. So we have the Ni sine theta I is equals to N2 sine theta R. Okay, well, maybe I can just write 1 and 2. All right, 1. Okay, so the critical angle, that means the refractive angle has to be 90. Okay, so N1 sine theta I is equals to N2 sine of 90. Okay, now that would give us N1 sine theta I is equals to N2. And now we have to find this one over here. So this is basically going to be our critical angle. Let me just change that real quick. Actually, I'll keep that the same. Actually, maybe I can just write it like that. So it will be N1 sine of that is equals to N2 sine of 90. And then I can say N1 sine theta of critical angle is equals to N2. So a sine theta is equals to N2 on N1. And therefore, our critical angle is equals to sine inverse of N2 divided by N1, which is equals to sine inverse of N2, which is going to be 1.47. And N1 is 1.50. Okay? So that means our critical angle should be what we have to prove. Okay, so sine inverse of 1.47 divided by 1.5. Yep, that is indeed 78.5 degrees. Okay, will total internal reflection occur at the core cladding boundary for this incoming ray? Support your answer with calculations. Now, of course, we have to first calculate the incident angle, and if that is less than the critical angle, then internal reflection will not occur. Okay, so let us start by calculating the incident angle first. Okay, so N1 sine of theta I equals to N2 sine of theta R. Okay, so our sine theta R is equals to N1 sine theta I on N2. So sine theta R is equals to, well, N1 is just air, so our refractive index is just going to be 1. So sine of 24 over 1.5. Okay, so our refractive angle would be sine of 24 on 1.5, and you have to do sine inverse of all of that. So sine inverse of all of that. Okay, so we get, let me just calculate that real quick. Sine of 24, 1.5. we get 15.73. Now, of course, we have to take it away. We have to take this amount away from 90. So incident angle is equals to 90 minus 15.73. So 90 minus 15.73. That is equals to 74.27 roughly. Now, since, well, our critical angle is 78.5, our incident angle is 74. So obviously it's not going, like the total internal reflection is not going to occur. So we can just state that since incident angle is less than critical angle, total internal reflection will not occur. Total internal reflection will not occur. Will not occur. Okay? Alright. A double slit is illuminated by light from a dual laser, which produces a light of two distinct wavelengths. This arrangement is shown in figure 17a. One of the wavelengths produced by the laser is known to be 650 nanometers. The other is unknown. Okay, the interference pattern on the screen shows that the second bright band for the light of known wavelength coincides with the third dark band for the unknown wavelength as shown in figure 17b. Yep. Okay. Determine the value of the unknown wavelength of the right light and show your reasoning. So that means this W over here is the same, so we can use that to calculate the unknown wavelength. So we can say that W is equals to N times lambda over D. And then we can say that 2 times, wait, 2, right? Yeah, so this is, 2. Our N will be 2, so 2 times 650 is equals to, what is this one? This one is going to be 2.5. Yeah, like this over here. Our N is going to be 2.5 for this one. So 2.5 times the lambda. Okay, so that means our lambda 2 is equals to 2 times 650 on 2.5, which is equals to, let's calculate that, 2 times 650, 2.5, so 520 nanometer. Okay, hopefully that made sense. So just that the width is going to be the same, so we can use it to our advantage and calculate this out. All right, a ray of white light is incident on a triangular glass prism as shown in figure 18. The glass prism has a refractive index of 1.5 and is completely surrounded by air, has a refractive index of 1. Okay, the white light disperses as it passes through the prism. On figure 18, draw the path of the light as it passes through a triangular prism and into the air. Show and label 2 rays, red and violet, and the colors opposite ends of the visible spectrum. Wait, no. Show and label 2 rays, red and violet, the colors. Okay. No calculations are necessary. Alright, so we just have to draw the rays of red and violet. Red will bend the least and violet will bend the most. So we can do like that and like that for red. Okay. Well, this looks kind of just one straight line. Can do like that and that. No, this is something like that. And this will be our red. And then our violet would be, it will bend the most. So it'll be like this and then like that. Okay. This and then like that. So this will be our violet. Okay. The glass prism is now completely immersed into a surrounding clear liquid that has the exact same refractive index as the glass prism. This is shown in figure 19. On figure 19, draw the path of light as it passes through the triangular prism and exits into the surrounding clear liquid. Well, if the refractive index is the same everywhere, then it would just be one straight line. There would be yeah, there would be no like there would be nothing like this. It would just be one straight line. Yeah, so it would just be like that. Just like this. Yeah. Okay. Yeah, because the surrounding refractive index and the refractive index of the glass prism itself are the same. So it will just be one straight line. There'll be no separation of the colors. Okay. Yeah. Okay, a series of regular straight water waves are incident on the barrier with a small opening. The water waves emerge on the other side as shown in figure 20. Li and Chang are discussing their observations of the water waves as they emerge beyond the barrier. Li says that the water waves diffract only if the wavelength is smaller than the gap width. Chang says that the extent of diffraction is independent of the wavelength. Evaluate the statements made by Li and Chang. Well, both of them are kind of wrong basically. So because Li is incorrect because, well, diffraction will occur regardless of its wavelength. I mean, regardless of the gap width. Like the extent will be different depending on other factors. I'll discuss that now. Chang says that the extent of diffraction is independent of the wavelength. No, so as I said, that diffraction will occur, but it also depends on the wavelength. Okay, so let me just write this down. So both Li and Chang are incorrect. Okay, so Li is incorrect because diffraction will occur regardless of the gap width. Regardless of the gap width. Okay? And Chang is incorrect because the extent of diffraction is proportional to lambda on width. So lambda is just the wavelength and width is the gap width. Okay? And hence, it does depend on the wavelength. Okay, so this proportionality over here proves both of them like wrong technically. Okay, hopefully that made sense. So diffraction will occur. How good the extent is of diffraction is determined by this over here. And of course, as you can see, like it's totally dependent on the wavelength, like wavelength right here. What am I doing? Yeah. So yeah, that's why both of them are incorrect. Okay. Yeah. Okay, two physics students are investigating the photoelectric effect by shining monochromatic light with a frequency of 1 times 10 to the power of 15 Hz onto a calcium plate. Their equipment is shown in figure 21. Figure 22 shows the graph of the relationship between the photocurrent and the reading on the voltmeter. Use the information on figure 22 to determine the maximum kinetic energy in eV of the photoelectrons. Well, that is just going to be 1.23, okay? 23 eV, 1.23. Okay? All right. Calculate the work function in eV of calcium. All right, so we know that EK is equals to HF minus phi, or the work function. So phi is equals to HF minus EK. So our H here is going to be 4.14 times 10 to the negative 15 because we have to calculate it in EV. Okay, so 4.14 times 10 to the minus 15 EV times by frequency, which was, 1 times 10 to the power of 15. 1 times 10 to the power of 15. And then take away, well, let me put that in the bracket, take away, what is the EK? 1.23, I believe. Yeah. Cool. So now if I were to calculate that in my calculator, 4.14 times 10 to the minus 15 times by 1 times 10 to the 15 minus 1.23. So I get 2.91 EV. Okay? Alright. The intensity of the light is now reduced to 50% of the original light intensity, and the experiment is repeated using the light of the same frequency on the calcium plate. So now the the intensity is now reduced. Okay, same frequency. The students obtain a new graph of photocurrent against voltage. Sketch the graph of the photocurrent and voltage for the reduced light intensity on the figure 23. Okay, so since the intensity is now reduced to 50%, our new graph would look something like this. Okay, no, not really. Yes, something like that. Okay, except this is straight line, not like this. Okay, let me try again. Let me see if I can get a better line going. Okay, whatever. Yeah, this will do. Okay, all right. The students change the light source to one with a different frequency. They observe that the photocurrent is zero and remains zero regardless of the size or the polarity of the voltage. Explain this observation. Okay, so in that case, the new frequency that they're using must be below the threshold frequency, right? Which means that there is not enough energy for the incident photons to overcome the work function. So therefore, yeah, photocurrent is zero, and yeah. So therefore, like, photocurrent is zero regardless of the size or the polarity. Okay, so we can write this down. So the new frequency must be below the threshold frequency, which means that the energy of the incident photons is not sufficient. Okay, is not sufficient to overcome the work function. To overcome the work function. Therefore, the photocurrent, is zero regardless of the size and polarity of the voltage. Polarity of the voltage. Okay. Yep. Right. Okay, so scientists carried out an experiment comparing X-ray diffraction with electron diffraction by analyzing the patterns produced by passing an X-ray beam and an electron beam through a thin polycrystalline aluminum foil. The X-ray photon energy and the electron kinetic energy are the same. Okay, the patterns produced have the same general appearance but different spacing as shown in figure 24A and 24B. The X-rays have energy 137 eV. Okay. Calculate the wavelength of X-ray beam, show your working. So we can just use E equals to hc on lambda. Okay, and we are calculating the wavelength, so hc on E. All right. And of course, since the energy is given in 137 eV, we have to use 4.14 times 10 to the minus 15. Sorry, that took me a long while. Yeah, 10 to the power of minus 15. And yeah, so lambda is equals to 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by E, which is going to be 137. So if I were to put that in the calculator, 4.14 times 10 to the minus 15 times by 3 times 10 to the 8 divided by 137. Let me change my mode to scientific again. So we get 9.07 times 10 to the minus 9 meters. Okay, 9.07 times 10 to the minus 9. Okay. Calculate the de Broglie wavelength of the electron. Show you're working out. Okay, so we have lambda is equals to h on p, right? And then we know that E is equals to half mv squared, which is equals to p squared on 2m. How did I get that? Well, I can express this as m squared v squared on 2m, right? And this will basically become p squared, which is the momentum squared. Oh, okay, let me change my eraser. Okay, so that means we have E is equals to p squared on 2m. So we have p squared equals to 2me, and that means p is equals to square root of 2me. Okay, so now we can easily calculate it. So we have the h value, we also have the momentum value. Well, we also have the m and then the e, of course, right? The reason why I had to convert all of this is because we didn't have the momentum, so I thought maybe just converting it would be better. Okay, and now we just have to substitute in the numbers. So the h would be 6.63 times 10 to the minus 34. All of that divided by the square root of 2 times the mass, which is 9.1 times 10 to the minus 31, times by the E, which is 137, times by 1.6 times 10 to the minus 9. Well, I mean, to the power of minus 19, not negative 9. Okay, so putting all of that in our calculator, square root 2 times 9.1 times 10 to the minus 31 by 137 times 1.6 times 1.6 times 10 to the minus 19. Okay, so I get 1.04 times 10 to the minus 10 meters. Well, 1.05. Okay, so 1.05 times 10 to the minus 10. Okay, explain why the patterns have different spacing when both beams have the same energy. Okay, well, the spacing is dependent on the wavelength, right? And the wavelength is determined by momentum. And just because energy is the same doesn't mean momentum is also the same. So because of different momentum, we have different spacing. Okay, so let us write that down. So the spacing depends on wavelength. And wavelength is determined by momentum and not energy. Not energy. Since the momentum is different, they have different spacing. They have different spacing. Okay? Because remember, whether it is particles like electrons or X-rays like photons and stuff, they are both connected by P equals to lambda. And as you can see, that the wavelength, which is why there is different spacing, is dependent on the momentum, not the energy. Okay? So that's why the spacings are different even though both beams have the same energy. Okay? Hopefully that made sense. Alright, sodium vapor lamps have often been used for the nighttime street illumination because the yellow light they produce penetrates mist and fog particularly well. When switched on, the sodium vapor lamp emits a characteristic yellow light of wavelength 589 Newton meter. Okay. Calculate the photon energy in EV for yellow light of wavelength 589 nanometer. Did I say Newton meter here? Nanometer, I mean, okay. Use C equals to this. Okay. So since we are calculating and dealing with photon, we have to use E equals to hc on lambda. And since we are calculating energy in EV, we have to use h is equals to 4.14 times 10 to the minus 15, right? So we'll have 4.14 times 10 to the minus 15 times by speed of light, which is 3 times 10 to the 8 divided by the wavelength, which was 589 nanometers times 10 to the minus 9. So let's put that in our calculator and see what we get. So 4.14 times 10 minus 15 times by 3 times 10 to the 8 divided by 589 times 10 to the minus 9. Okay, so I get 2.11 EV. 2.11 EV. So draw an arrow on figure 25 to show the energy level transition that takes place to produce the characteristic sodium yellow light of 589 nanometers. Okay, well, yeah, it's just going to be from here all the way down here. Okay? Because of, yeah, energy. Alright, yeah, hopefully that made sense. The ionization level for sodium is 5.14 eV. A sodium atom in the ground state absorbs a photon that ionizes the atom. So, in the ground state, okay? Draw an arrow on figure 26 to show this transition. So, it's now absorbing, so an arrow is going to point upwards, and it's because it's going from ground state all the way to the ionization level. It's going to go from 0 all the way to 5.14 because that is the ionization level of sodium. Okay, hopefully that made sense. All right, question number 19. How many questions do we have? This is the last one. I think so. Yeah, okay, cool. So question 19, the last question. Okay, students are building a model of a part of a children's game. It consists of a spring that fires a block of mass m along a frictionless track. The track curves upwards and the block stops for an instant at a height h above its original position. It then slides back down the track. The experimental setup is shown below in figure 27, with the spring shown in an uncompressed state, where L is the natural length of the spring. The spring constant is K. Okay. The spring is compressed a distance x and then released. Model the block as a small point mass, the surface as frictionless, and the spring as both massless and ideal. Show that H is equals to this. Outline the steps of your reasoning. Very well. So we are basically just converting all the spring potential energy into the potential energy, right? So all of the initial spring potential energy is going to be the final potential energy because that's where it's going, right? So we can say that half kx squared is equals to mgh, right? Because this is the initial spring potential energy and this is the final potential energy. So they both are going to be equal. And to explain our reasoning, we can say conservation of energy. Conservation of energy. Okay? And now we can just solve. So H is equals to kx squared on 2mg as required. Okay? If the spring were not massless, what would be the effect on the height h? Calculations are not necessary. Give your reasoning. Well, the height h would be pretty much reduced because now spring itself needs to be accelerated, right? Like if the spring has a mass, then all of the force has to first accelerate the spring and then accelerate the block as well. So basically, rather than just accelerating the block, now we are accelerating the spring as well. So there will be some energy lost to that. So we can say that the height h would be reduced as now mass of spring and the mass of block, and the block needs to be accelerated. Okay. Rather than just the block. Therefore, the max height reached would be lesser. Okay? Alright, so the students know that the value of m is 150 grams, but they do not have a value of k. They set up an experiment to find the value of k by varying the compression of the spring and observing the resulting height h. Identify the independent and dependent variables of their experiment. Very well, so since we are varying the compression, that is going to be our independent variable, so we can say compression, which is going to be the x. And depending on the compression, we will get the height h. So height is going to be dependent. Height h. Okay? The measurements that the students record are tabulated below. Teacher suggests that they plot the values of h on the y-axis against x squared on the x-axis. Give a reason why it would be better to plot the values of x squared rather than x on the x-axis. Well, it would give us a straight line rather than having a graph, like a quadratic graph essentially. So it would result in a straight line. It would result in a linear graph. Okay? Using the values in the table below, construct a graph with h on the y-axis and x squared on the x-axis. Include the error bars and a line of fit. Okay, so first we have to start by labeling h in meters and x squared meters squared. Okay, and now we have to divide up the grid. So let us start by the x. So we have the minimum value is 0.0030 and maximum is 0.0120. Okay, and how many do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, I guess taking a gap of 6 would do it because, yeah, if we take a scaling of 0.003 to go from here all the way to there, then I guess 6 would do, right? Like the gap of 6. So 1, 2, 3, 4, 5, and 6. Okay, so let's draw a line here. Okay, it's a way off, but like that. Okay. 1, 2, 3, 4, 5, 6. Another one here. Like so. 1, 2, 3, 4, 5, 6. Another one here, like there. Okay, one to the right. And the last one. 1, 2, 3, 4, 5, 6. Like so. Okay. So I guess that's that for the x-axis. We have to do similar thing for the y-axis. Okay, but before that, let me label all of this. So 0.0030, 0.0060, 0.0090, 0.0120, and then so on. And now for y, or the height, we are going from 0.04 all the way to 0.21. And how many do we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay. I guess dividing it into a segment of 6 would be ideal. So I guess we can do 4, like 4 gaps. So 1, 2, 3, and 4. Like that. 1, 2, 3, and 4. Like that. 1, 2, 3, and 4. Okay. 4. 1, 2, 3, 4. Okay, I think that should do it. Let's number so that we can find out. Okay, so we are going from 0.04, so 0.04, 0.08, 0.12, 0.16, 0.20, 0.24. Okay, I think that is quite perfect. So let's start. So 0.003 and to 0.04. So it would be right here, basically. And then in H, in the y direction, we have a scale of 0.01 for the marginal error. And here we'll have 0.0001. Okay, so we have divided into 6, right? So 0.0030 divided by 6. Okay, so this 1 is going to be, hold on. Okay, so 1, like this gap over here is going to be 0.0005. So 0.0005. And we are taking a gap of 0.001. So we have to times it by 2. So 2 widths essentially. So we'll go from here all the way to here. Okay. Like so. That is going to be our error bars here and here, like that. Okay. And then we have, what is it, 0.0059 and 0.11. So 0.0059 would be somewhere here, and this should be right here, somewhere like this. Okay. One up, and then one down, and then 2. So that's 1, and that's 2. So something like that. Like that. Okay, and similar here. Nope. Like that. Okay. Next one is 0.009 and 0.14. So 0.009 and 0.14 is going to be here, like there. Okay. That. Like that. Okay, no, this one, it's not quite nice. All right. Like that. Like that. Yeah, these are the most time-consuming questions. All right. Okay. And then the last one is 0.120 and 0.21. So somewhere around here. I mean, now that I think about it, the scaling looks quite nice, which is always good. Okay, what is this? Just to copy and paste. What? Paste. Okay. All right, so that's that. And now we have to draw a line of best fit. Okay, cool. So I guess we can go like that. Something like that would do, right? Okay. That will be my line of best fit. Okay, yeah, so that's that for this graph question over here. Anything else? No. Okay, cool. Measure the gradient of the graph from the line of best fit. Okay, so now we have to take up 2 coordinates and yeah, get the results that way. Oh, actually, well, we have 2 coordinates quite vividly. We can take in this one and this one over here because they are basically on the point, right? So we will take 0.0090 and what is it? 0.15. And then the second coordinate we have is 0.0120, 0.0120, and 0.2. 0.2. So our m is going to be 0.2 minus 0.15 divided by 0.0120, take away 0.0090. Okay? So let us calculate. So 0.2 minus 0.15 divided by 0.0120, take away 0.0090. So I get 16.67. 16.67. Use your result in part F to calculate the value of spring constant K. Okay, so our H is equals to, what was it? It was kx squared on 2mg. So kx squared on 2mg. Okay, now, you see this x squared term over here? We can write this as k on 2mg times by x squared. Because we are plotting the graph against x squared and not x, this over here will be our gradient. Does that make sense? Okay, so gradient is equals to k on 2mg. Okay, so a k is equals to 2mg times by the gradient, which is 2 times the mass. What is our mass? Mass. Where is the mass? Oh, right here. 0.15. Okay, cool. 0.15 times by 9.8 times by the gradient, which is 16.67. And let us finally type all of that. So 2 times 0.15 times 9.8 times that. We get 49. So 49 Newton per meter. All right. Okay. So that is the end of the examination. Thank you for watching. Hopefully you learned from this video, and I'll see you in the next video. Bye-bye.